But the weirdness didn't stop there. Building on earlier discoveries, Niels Bohr refined the wave-particle mystery into a usable principle, the principle of complementarity. This principle states that quantum objects have two sides, a wave side and a particle side. And it is this wave-like nature that makes qubits, short for quantum bits, possible in quantum computing. In a traditional computer, two electrical states are used for bits to process and store information. Switches which are either on or off, which is represented by a value of either 1 or 0. Traditional computer bits are solid, definite things, like a coin on a table that is either heads or tails. But in a quantum computer, a good analogy for how a qubit behaves is more like a plucked guitar string. When you pluck a string, you don't hear one flat, pure tone. You hear a fundamental note mixed with several quieter, higher overtones. The string vibrates as one long arc, but at the same time, it vibrates in two smaller halves, and it's also vibrating in three even smaller parts. All these different waves live on the same string at the same time. To describe the string's position, you cannot point to one spot. You must describe the entire complex pattern of all those vibrations combined. In physics, this overlap of waves is called superposition. This is exactly how a qubit holds multiple pieces of data at once. Because these waves can overlap, a qubit isn't just a 0 or a 1, it's a complex coexistence of both, a 0 and a 1 at the same time. This allows the computer to explore an enormous number of possibilities at the same time. While the computer is thinking, it stays in this wave-like state, exploring every path at once. But the moment we measure it or ask for an answer, the wave function collapses into a single, definite, particle-like state, a 0 or a 1. At that exact moment, the wave-like superposition vanishes. Without this collapse, we could never get a readable result. It is this wave-like behavior that gives quantum computers their extraordinary power. Bohr's daring ideas forced us to accept a radical new reality, one that we are only now beginning to harness through the power of quantum computing.